Hello everyone, it's nice to be in touch, such as it is, and this is, as promised, the video that I'm making that will hopefully get you up to speed with vectors. So I'm pretty sure that you all know what a vector is. It is when you draw it, it looks something like this, and a vector has what we call magnitude and direction. So the magnitude is simply its length, and the direction is the way in which it is pointing. Some examples of vectors are the wind, the motion of a car, or a plane, which is in 3 dimensions, or pushing a box up an inclined plane. So here you see an example of a vector which is drawn in what we call standard position. And that simply means that it originates from the origin and it points up in whatever direction it is. And if we call this vector v, and we usually indicate vectors with a little arrowhead over the top, then we said that a vector has 2 characteristics, right? Magnitude and direction. So for this particular vector v, its magnitude is simply its length. And the way we indicate magnitude is like this. The way we indicate its angle or direction is with the angle theta, which is between the positive x-axis and the vector itself. So here what you see is a vector which is listed as a comma b, and we have these braces rather than parentheses to indicate that it's a vector. So for this particular vector, we see that its magnitude is simply equal to the square root of a squared plus b squared, and the angle theta that it makes is simply the arctan of b over a. So here's a specific example. Suppose the vector u is the vector 3, 5. And we want to know what its magnitude is. So you know enough about this to know that the magnitude is going to be the square root of 3 squared plus 25 squared, or the square root of 34. And the angle theta is simply going to be the arctan of 5 over 3. So again, we know that the magnitude of this vector is the square root of 34. And suppose what we want is a unit vector in the same direction. Well, you should be able to believe that what a unit vector is the magnitude is equal to 1. So, since the magnitude of this vector u is the square root of 34, a unit vector in its direction would simply be this. It would be 3 over the square root of 34, comma 5 over the square root of 34, which actually is the same as 1 over the square root of 34, which is the magnitude, times 3, comma 5, which is really the same as 1 over the magnitude of u times u itself. So now let's talk about the kinds of operations that we can perform on vectors. And some of the operations which luckily are really easy are addition and subtraction, and which we'll look at an example of right now. So let's suppose we have these 2 vectors, u and v, and we want to consider what the sum is. In other words, what does u plus v equal? So why don't you press pause, make sure you guessed correctly, and then turn it back on again. Yes, I bet you're right. It is as easy as you think. When you add the vectors, you simply add up the x components and you add up the y components. And when you subtract, you do the same thing. So u minus v would be 5 minus 3, and minus 2 minus 7. And that's as easy it is to add and subtract vectors. So let's look at the geometry of adding vectors. So what you see here are two vectors, u and v, both written in standard position. And what we want to know is, how do I add them geometrically? And so the result is actually pretty cool. We just take u, or it could have been v, and draw it so that the tail is at the head of the other one. In other words, I'm going to draw u like that. So u has the same magnitude and the same direction. And then all I'm going to do is connect them. And I connect them as so. And that resultant vector is u plus v. It's kind of cool. So the next style, or the next operation that we look at, is scalar multiplication, which we actually looked at already when we were talking about unit vectors. And the way this works is, suppose you have any vector at all, and we'll call it v, and suppose c is a constant, and all we're going to do is say, what happens if I take c and multiply the vector? Well, again, this is very simple. You just multiply each component by c, and we get the resultant vector. So another way of representing vectors is using what's known as a linear combination. And this requires that we define two very special vectors, I and j. And these are each unit vectors. I is simply the vector 1, 0, and j is the vector 0, 1. So these are unit vectors, I pointing in the x direction and j pointing in the y direction. And all this enables us to do is that if I have any vector v, again, defined as a comma b, it can be written as a times vector I plus b times vector j. And that's known as a linear combination of vectors. So now the last operation on vectors that we'll look at is the dot product. And the dot product is really the most interesting one of all of these. It's one that is really not familiar at all. And the dot product of two vectors is written like this. And what it equals is the product of the x values added to the product of the y values. So as this note indicates, and as you should observe from this result, the dot product of two vectors is a scalar and not a vector. Yeah, I'm sorry, I realized I incorrectly wrote dot. That should be corrected now. Sorry. So the following properties of the dot product, as I say here, should be pretty easy to believe. They should look familiar to you. And I would really encourage you to kind of pause this video and practice using the definition. The definition is right here to prove them. So I'll simply write them out and you can try proving them when you have a chance. So as I've said, these four rules, and there are a few more that are included in your notes, these four rules follow immediately from the definition. of the dot product. And they're all fairly simple to prove, and as I've said, try proving them. Now, what's kind of neat is that the dot product gives us a method to find the angle between two vectors. So imagine that we have two vectors that look as follows. So here we see two vectors, u and v, and the angle x between them, which is what we want to find. And what we'll notice, what we'll prove, is that this is the relationship, that the cosine of x is going to equal the dot product of u and v divided by the product of their magnitudes. So that seems kind of out there. And the way we're going to prove this is by using the law of cosines, which is pretty cool. But first we have to look at the vector v minus u. And I'll show you how that works. So given the vector u, the vector minus u is shown in red, and it's simply the same magnitude, just in the complete opposite direction. But notice now we have drawn minus u and v in the way that we can add them. And so the sum of v plus minus u will look like this. And so that blue vector is the result of v minus u. So now observe this triangle that we have with the black, red, and blue vectors. One length is u, the other length is v, and the other length is v minus u, and v minus u is opposite the one angle that we have, x, which is what we're trying to find. And so here's where we use the law of cosines, and you should be able to follow the result that I'll write down. So hopefully your memory is good, and you see that what I've written down here is just the exact law of cosines using angle x as kind of my anchor. What we do now is we're going to use property 3 of the dot product. So you can check that in your notes or go back and see what it is in this video. But that tells us simply that if we have any vector u dot u, that's equal to the magnitude of u squared. And if I look on the left side, that enables me to write the line as follows. Okay, follow that? Now what we're going to do is apply property 2 to the expression on the left. And it has to be done twice, and so you'll have to figure that one out a little bit. But I'll use property 2, and then I'll use property 3 a little bit. And ideally, you should be able to follow the sequence that I am going to show you now. See how that line works? And then I use it again, and I get the following line. And using that property again, I'll get the next line. Okay, hang in there, we're almost done. Notice how much I can simplify. I have a v squared here and v squared here. I have a u squared here. I have a u squared here. I have a minus 2 here. I have a minus 2 here. And so if I solve for cosine of x, ta-da, here's what we get. Okay, let's have a drum roll. That's the result we were looking for. And that gives us a way to find the angle x between two vectors u and v. So as an example, let's look at this picture where we have u and v as defined, and we're looking for angle theta, which is the angle between them. So let's do some preliminary work. We know that u dot v is equal to minus 6 plus 35, which is equal to 29. We know that the magnitude of u is going to equal the square root of 34, and the magnitude of v is equal to the square root of 53. So therefore we know that the cos of theta is equal to the dot product of u and v over the magnitudes. There we go, which gives us 29 over square root of 34 times the square root of 53, and if you use your calculator, that's about equal to 0.6831. So theta is the arc cosine of 0.6831, which is about equal to 47 degrees. And that's how we solve these problems. So one of the things that is a little different about vectors is when we talk about vectors being perpendicular, instead of using the word perpendicular, we use the word orthogonal, which simply means perpendicular. And what we want to try to do is get some idea of why or when two vectors will be perpendicular. And we know that vectors will be perpendicular if the angle between them is 90 degrees. Right? Two vectors are orthogonal if the angle between them is 90 degrees. And we know that the cosine of 90 degrees is 0, which implies that if two vectors are perpendicular, their dot product must be 0, right? And that all follows from the fact of this result that we have proven. If cosine of x is 0, then that means that u dot v must be 0. And cos of x is 0 exactly when the two vectors are orthogonal. So let's just look at this fairly simple example. We have two vectors here given u and v, and we're curious, would like to show whether or not they're orthogonal. And two vectors are orthogonal if their dot product is 0. And so we look at the dot product of u and v, and we notice that it's going to be minus 30, minus 30. So what's your conclusion? Yes, of course, those vectors are not orthogonal because the dot product is not equal to 0. So let's make a small little change here, and let's just say that this was a plus 10. Now the dot product of u and v is going to be 30 minus 30, which is equal to 0. So these two vectors are indeed orthogonal because their dot product is 0. So that concludes the discussion on vectors. I hope this helped you. So watching this video and reading those notes hopefully should be sufficient for you to get a good understanding of vectors. Then you can begin the problems. And remember, any questions during this lecture or doing the exercises, just post something in the discussions part of Canvas, and I will get back to you as soon as I possibly can. Thanks. See you next time.